Right, so we're talking about net ionic equations, and one of the things I want to point out is what a net ionic equation does. It shows us what is actually reacting, because when we have a reaction, there's a lot of things that are kind of hanging around in the mix, but they might not actually be undergoing any kind of change. So the net ionic equation allows us to simplify things so that we are only looking at what's reacting. Having said that, in simplifying things, we often end up with something that a lot of students find quite complicated, and it really should not be. It does require us to understand a few things, and we're going to try to emphasize that as we go. So we're going to start with a synthesis reaction, because I think at that point it makes the most sense. If I have a fairly simple synthesis reaction between a sodium and a chlorine to produce sodium chloride, and of course I don't have the states in here, but I'm using the atoms or the elements as I know them, including diatomic chlorine. Sodium undergoes a change of forming an ionic bond. So it starts out as a neutral atom and finishes as a +1 charge. And when chlorine, something similar except opposite, it starts out as a neutral atom and goes to a -1 charge. So I can look at both of those and say they have changed and they have become something new. They've gone from a neutral to an ion. So they both have undergone a reaction. But if I look at other reactions, that might not be the case. Now I need to pause here, and I wasn't ready for it, but one of the things that's going to be really, really important, and so if you're writing things down, this is definitely a thing to write down, because this is one of the keys to the whole operation. If you have an ionic compound that is dissolved, it will exist as separated ions. So an ionic bond only really functions as a bond when that compound is a solid. Once you dissolve it into water, for example, and it becomes aqueous, now the ions exist in free form. So for example, going back to my sodium chloride again, when I write sodium chloride aqueous, what's actually going on is I have sodium ions floating around and I have chloride ions floating around. If I write calcium chloride, I've got calcium ions floating around and they've got a 2+ charge, and then I will have chloride ions floating around, but there will be twice as many of those because they have half the charge. And I want you to pay particular attention to what's going on with the chlorine, because that little subscript 2 in the calcium chloride does not stay as a subscript. And this is one of the places where people run into a lot of problems. They struggle to convert the formula into ions. If I had something really big and weird looking like iron, iron 2,3 sulfate, then, well, there's 2 ions of iron and there's 3 ions of sulfate. But you'll notice where the subscripts go, because what they represent in the formula and how you would write that as individual ions. If an ionic compound is not dissolved, if it's then in solid form, then those ionic bonds are still in play, and I would have the compound as I would expect the compound to be. It would be together in that solid form, not separated as ions. Yes, it exists as ions, but they're all together. Okay, another way to look at this in picture form, and I've just done the sodium chloride, is that the ions come out of the solid, out of that lattice that we talked about way back, and now it exists as ions. And those ions get surrounded by water because that's what dissolved means. Okay, trying a different kind of reaction, in this case a single displacement reaction. If I look at this one, so I've got copper 2 chloride with zinc reacting to form zinc chloride and copper. If I break it down and look at each element, each type of atom, copper starts out in an ionic compound, starts out as a +2 and becomes a neutral atom on the product side. That has undergone a change. Zinc, likewise, starts out as a neutral atom and finishes up in an ionic compound, so it has also undergone a change during that reaction. But chlorine starts out in an ionic compound and finishes in an ionic compound where its charge has not changed. The only thing that's changed is who it's partnered up with, but we have an ionic compound dissolved in both cases, which means it's not the zinc and chlorine are actually together, they're floating around as separate ions. So the chlorine undergoes no change during that reaction, which means it's not actually reacting. It's hanging around, it's making sure that charges get balanced, but it's not actually changing any reaction or changing in the reaction, which means we call that now a spectator ion, which means it's just hanging around. So if I look at all of those things and I break them down using that thing that we just talked about, that ionic compounds, when they're dissolved, they exist as ions, then it starts to look like this, which right away looks more complicated when I said this is a way to simplify a reaction. But if I get rid of the spectator ions and then only have the stuff left over, which is only the things that are actually involved in reaction, then the chlorines are going to be disappeared from either side, and I'll be left with this. Now, please understand, this reaction could not happen in this way simply because you cannot get a bottle full of copper 2 ions. What you can get is some copper chloride, but it doesn't matter if it's copper chloride or copper 2 bromide or copper 2 sulfate. Anything would technically behave in the same way because the reactions between the copper ions and the zinc. Okay, our main focus is going to be on double displacement reactions because those are going to be the ones that we are going to be typically using. So if I have this, I can take a quick look and say I've got things that are aqueous and dissolved, so I will be applying that thing we talked about earlier where the dissolved compounds exist as ions. And then I've got something that is undissolved. It is a solid. That means it does not exist as separated ions. So if I want to look at the reaction in this way, the reaction is taking things that are dissolved and turning them into, or combining them to make things that don't dissolve. So that's the reaction that's actually going on, forming that precipitate. Okay, breaking it all down as much as I can because there are certain things I will not break down, but the potassium and the iodide I can break down. The lead and the nitrate I can break down. The lead iodide I cannot. And the potassium nitrate at the very end I can. So that starts looking kind of complicated, but there's a lot of spectator ions. The potassium, spectator ion. The nitrate, spectator ion. The things that start out in ionic form, in aqueous form, and finish the reaction in solid form are not spectators. They cannot be crossed out. And you'll notice the lead 2 iodide I did not write as separate ions because it's not dissolved. Same thing with the other half of that compound, or the other elements involved in that compound. So if I eliminate the spectator ions, I get rid of a bunch of things that exist in aqueous form on both sides, exist as ions, ionics, things in both sides, and I end up with the net ionic equation, the ions that are actually reacting to produce the significant product. If I made that bigger and weirder looking and so on, because we ran into that before with the calcium chloride and where do I put the 2, well, I'm going to start with here. I'm also going to write it slightly differently, so I'm not writing out the whole thing. You are more than welcome to write it out in detail. What I want to do though, I don't want to call it a shortcut, but I want to simplify what I write down. I'm going to pay particular attention to the things that are aqueous, because those are going to be the spectator ions, aqueous on the product, aqueous on the reactant side, aqueous on the product side, and even more attention to the things that start out aqueous on the reactant side but finish up as solids, because those are the things that are involved in the actual reaction. Okay, if I start thinking about the ions that I need to have in order to make the solid, I need to have the carbonate, the CO3, and the aluminum, which means I can eliminate the sodium because it's aqueous on both sides, and I can eliminate the chlorine because it's aqueous on both sides. If I eliminate those ions, and I don't see the ionic charges on those right now, but it is definitely there, I'm left with ions of CO3, which is a 2- ion. I'm left with the ion of Al, aluminum, which is a +3 ion, and I'm left with the solid product on the other side. Now, I haven't really emphasized, but the 3 in front of the first reactant is still there. The 2 in front of the aluminum is still there. So when I go to rewrite my equation as a simplified version of the net ionic equation, then I have this, where the balancing numbers tag along. By the way, if there was a little number that became a big number and then a big number in front of that, yes, it would carry forward, much like the 3 with the sodiums, but there was 2 sodiums, now it becomes 6 sodiums on the product side. That would also apply. Okay, this one, I'm going to leave you with, or these ones, I'm going to leave you with a couple for practice, and we'll take that up in class. I also want to leave you with this. I'm not really going to read it through, but I recommend you pause it and read it through, or you write it down perhaps, and then the steps for getting the net ionic equation are also nothing that we didn't already do, but as I said before, some people really struggle with doing this on their own, so it's worthwhile having as much information and detail as you can. Finally, where are we leaving it from here? Well, or where do we go leaving it, and where do we go from here? Really, what it is writing the net ionic equation. 3 things you need to have for a net ionic equation. 1 is it needs to be net. Get rid of all the spectators. 2 is it needs to be ionic. You can't just cross out the things that you don't need and leave it and think I'll not notice. I will absolutely notice. And 3, it needs to be a proper chemical equation, which means it needs to be balanced. But that's how we get the net ionic equation. And then we'll practice some of this in class. It's not going to be something we do an awful lot, but it is a pretty important thing. And we'll talk to you later.